Alright, this is part 2, I guess, to a much earlier video on partial fractions. The idea of partial fractions was to take a fraction like this, where the bottom is nicely factorized, and to split this guy into a sum of, I guess, smaller fractions, a bit like this. And what we saw last time was that if the bottom was a quadratic, like what we have in the x minus 2 or square, the top has to look linear, so it might have an ax plus a b, not just a constant, whereas the one on the right, because the bottom's just linear, the top is just a constant. Alright, that's how we did it maybe last time, but there's actually a special case when the bottom is a perfect square, or some other power. Right? We can take a closer look at this guy, and what I'm going to do is write it really weird. I'm going to minus and plus 2a on the top. Right, and you'll see in a moment why we're going to do this. The idea is to then factorize the ax minus 2a into a bracket x minus 2. Okay, and the rest of the mess stays. But what we can then do is split the fraction along there, and the x minus 2 in brackets will actually cancel one copy of x minus 2 on the bottom, and you end up with something like this. Okay, and what makes that nice is that if you look at the fraction on the right, the 2a plus b is just a constant. And so what that means is if we go back to the original fraction, the big one, we can rewrite that actually as a over x minus 2 plus some constant. Now I've used b again, but it's just a label, it's just a constant, the pink one, over x minus 2 all square plus c over x plus 1. Now why we might prefer doing it this way rather than just using the ax plus b thing is that, well, the end game is being able to integrate these things easier, and I think the integration falls out a little bit nicer if we don't have any x's on top. It just makes things a little bit easier, as you'll see soon. Right, so let's solve this one, and then we'll do the integration afterwards. So we'll use this guy here. What we're going to do with this is we want to have a common denominator on the right. So we pretend we're adding those fractions again, so we're targeting that denominator. So let's look first at the a over x minus 2. It needs another copy of x minus 2 as well as x plus 1. So we're going to get that multiplying by the a. Then move on to the middle guy. I think this guy just needs the x plus 1, so we add that in. And then the last one needs both copies of x minus 2. So we've got to multiply c by x minus 2 all square. So that's our numerator. And so once again, we need to equate the numerators. So 8 minus x equals that whole top. And so we solve for those a's and b's and c's. We put in x equals 2. That's going to kill those ones. So we get on the right 3b equals on the left 6. So that means b is 2. We can put x equals negative 1. That kills those two. So on the right we have negative 1 minus 2, which is negative 3. Square it, you get 9. So 9c equals on the left just 9. Then we get c equals 1. Going through this a bit quicker this time because I think we saw this stuff last time already. And finally, we can equate x squared coefficients, I guess. So we only have 2 of those. We have those 2. So that means that a plus c must add up to, well, there's no x squares on the left, so they must add up to 0. And because c is 1, a must be negative 1. Okay. So that's all the same as what we did last time. Okay, so we have those a's and b's and c's. Maybe write that down if you need to, because now we're going to try and integrate that original thing by integrating the partial fraction decomposition with the a and b and c put in. So the negative 1, the 2, and the 1. And again, because there's no x up the top, all of these are actually immediately doable. You don't have to do anything to them. So the first one's just a log, the second one's the most normal integration ever. And the third one's also just a log. Okay, and so that falls right out for us. So the aim of this weird A and B and C thing for the perfect squares is that I think it makes this integral step a lot easier. Okay, so that's how we handle that particular case. So have a go at that, and I'll see you next time.